Hello and welcome back to my Amateur Radio General License course. It's a wonderful day in the amateur radio neighborhood, and it won't be long until you can fire up your own HF rig and throw out your call sign and your CQ. Are you ready to learn? Well, let's get started. This is the Amateur Radio General Class License course, Lesson 9, Part 1. I'm your instructor, Gary Stevens. That's Kilo Echo 2 Gulf Sierra, KE2GS. Today we're going to go over sub-element G9. There's 4 exam questions out of the 4 groups of 54 questions. This is the 2019 to 2023 General Class FCC Element 3 question pool that went into effect July 1st, 2019. In Part 1, we're going to be covering antennas and feed lines. We're going to cover G9A, which is the antenna feed lines, characteristic impedance and attenuation, SWR calculations, measurement and effects matching networks, and also G9B, which is basic antennas. So let's dive into G9A, antenna feed lines, characteristic impedance, attenuation, SWR calculation or standing wave ratio calculation, measurement, and the effects of matching networks. So coaxial cable, or coax as it's sometimes called, is a type of electrical cable that consists of an inner conductor that's surrounded by a concentric conducting shield, and the two are separated by an insulating material that's known as a dielectric. Without going into some heavy-duty math, we'll just talk about the determining factors of the impedance. So, the most important factors is the diameter of the conductor, center conductor, and the type of dielectric material that's used, and also the material used in the shield. For the exam, you need to know that the distance between the centers of the conductors and the radius of the conductors is the factor that determines the characteristic impedance of a parallel conductor antenna feed line. For the purpose of amateur radio, we usually deal with 2 types of impedances of coaxial cables. They're 50 and 75 ohms. For the exam, you need to know that the typical characteristic impedance of a coaxial cable used for antenna feed lines at amateur radio stations are 50 and 75 ohms. Another type of transmission line or antenna line is called a window line, or it's often also referred to as a ladder line. It kind of looks like a ladder, it kind of looks like windows. But for the exam, you need to know that the typical characteristic impedance of a window line parallel transmission line is 450 ohms. You'll often hear the phrase reflected power, and it boils down to being kind of a difference between the feed line impedance and the antenna feed point impedance. For the exam, you need to know that a difference between feed line impedance and antenna feed point impedance might cause reflected power at the point where the feed line connects to the antenna. As you may recall from earlier discussions and the technician class, attenuation is basically just a loss of power. So for the exam, you need to know that attenuation increases in the coax cable as the frequency of the signal it is carrying increases. This is also known or referred to as the skin effect. When calculating our radiated power out of our antenna, we need to know how much we're losing in our feed lines. And it's expressed in decibels. All the losses and gains are expressed in decibels. For the exam, you need to know that the units of RF feed line loss usually expressed in decibels per 100 feet. And we're always talking about SWR, standing waves, ratios, um, having a matched antenna with your feed line is important to get a good SWR. For the exam, you need to know that antenna feed point impedance must be matched to the characteristic impedance of the feed lines in order to prevent standing waves on an antenna feed line. Matching networks are great, but if they're incorrectly matched, then they're not so good. For the exam, you need to know that if an SWR on an antenna feed line is 5:1 and the matching network of the transmitter end of the feed line is adjusted to 1:1, SWR, then the resulting SWR on the feed line is still 5:1. Exam, you need to know how to calculate the standing wave ratio, and it's basically we take our non-reactive load and divide that by our feed line. So in this case, we have a non-reactive load of 200 and a feed line of 50 ohms. So we divide the 200 by 50, and we get a 4:1 SWR ratio. Alternatively, you could just remember that the standing wave ratio that will result when connecting a 50 ohm feed line to a non-reactive load having 200 ohm impedance is 4:1. Using the same math, you need to know on the exam that the standing wave ratio that will result when connecting a 50 ohm feed line to a non-reactive load having 10 ohms is 5:1. My apologies, I just noticed that this in the previous slide was VSWR instead of SWR. So please excuse that. For the exam, you also need to know that the standing wave ratio will result when connecting a 50 ohm feed line to a non-reactive load having 50 ohm. The impedance is 1:1, or the ratio is 1:1. I don't like the way this is worded, but it is what it is. For the exam, you need to know the interaction between a high standing wave ratio and a transmission line loss is if a transmission line is lossy, high SWR will increase the loss. And finally, we need to know that the effect of a transmission line loss on standing wave ratio measured at the endpoint or input to the line is the higher the transmission line loss, the more the standing wave ratio will read artificially low. We want a 1:1 match. That's perfect, but in reality, we never get perfect. So next up is our basic antennas, general section 9B. When transmitting, the radiant energy can not only heat up the antenna, but it can also heat up objects near the antenna. So for the exam, you need to know that one disadvantage of a directly fed random wire HF antenna is you may experience RF burns when touching metal objects near your station. To a keen observer, you may notice that a lot of antennas have radials that point downward. And one of the reasons they do that is for impedance matching. For the exam, you need to know that a common way to adjust the feed point impedance of a quarter wave ground plane vertical antenna to approximately 50 ohms is to slope the radials downward. That's a neat trick, right? With an antenna, omnidirectional just means that it can receive or send signals in all directions at the same time. For the exam, you need to know that omnidirectional in azimuth best describes the radiation pattern of a quarter wave ground plane vertical antenna. One of the nice features of a dipole antenna is its ability to create a figure-8 pattern of radiation. For the exam, you need to know that the radiation pattern of a dipole antenna in free space in a plane containing the conductor is best described by the sentence, "It is a figure 8 at right angles to the antenna." Might imagine the height of a horizontal antenna affects its radiation pattern. For the exam, you need to know that the antenna height affects the horizontal or azimuthal radiation pattern of a horizontal dipole HF antenna. For example, if an antenna is less than a half a wavelength high, the azimuthal pattern is almost omnidirectional. For vertical antennas, the ground plane should be laying on the ground for best results. However, that's not practical because you can imagine running over it with their mower. So for the exam, you need to know that the radial wires of a ground-mounted vertical antenna system should be placed on the surface of the earth or buried a few inches below the ground so your lawnmower blades don't eat them up, or vice versa. Another thing that's affected by the height of a dipole antenna is its impedance. For the exam, you need to know that the feed point impedance of a halfway dipole antenna changes as the antenna is lowered below a quarter wave above ground. When this happens, it steadily decreases. In other words, the impedance decreases steadily. Another thing that affects the impedance of a half-wave dipole is how far the endpoint is from the center, or how close it is to the center. Changing that can vary the impedance. For the exam, you need to know that the feed point impedance of a half-wave dipole changes as the feed point is moved from the center towards the ends. When this happens, it steadily increases. You can see by this diagram that the vertical antenna, the radiation pattern tends to go into the ground quite a bit and it can be absorbed, whereas the horizontal just goes outward. For the exam, you need to know that an advantage of a horizontally polarized HF antenna as compared to a vertically polarized HF antenna is that it has a lower ground reflection loss, or losses. Out your pen, paper, and calculator. They want us to know how to approximate the length of a half-wave dipole antenna that's cut for 14.250 megahertz. So a half-wave dipole length in feet is equal to 468 divided by the frequency of megahertz. So given that we know the frequency of 14.25 megahertz, the length would be 468 divided by 14.250, which comes out to 32.8421053 feet, which is approximately rounded off to 33 feet. So for the exam, you need to know that the approximate length for a half-wave dipole antenna cut for 14.250 megahertz is 33 feet. This time they want us to calculate for 3.550 megahertz. It's the same formula, you know the drill. You plug in the variables and we come up with, when we do the math, we come up with 131.830986 feet, which we round up to 132 feet. For the exam, you just need to know that the approximate length for a half-wave dipole antenna cut for 3.550 megahertz is 132 feet. Trying to trip us up by throwing in a quarter-wave antenna, but quarter wave is only half of a half-wave. So we use the same formula. We calculate it. We get for the number 28.4 megahertz, and we come up with 16.478872 feet, and we just divide that by 2, and then we get our quarter wave, which is 8.2394366.2 feet, and we round that down this time to 8 feet. So that is it. So that concludes Lesson 9, Part 1. Congratulations, you made it through. I hope you've enjoyed today's lesson. If you like this video, give it a thumbs up. Also, I invite you to subscribe to this channel if you haven't already done so. Until next time, stay safe and never stop learning.